In previous tutorial, we learned how to divide one polynomial by another polynomial. And now we will learn remainder theorem of Bezout. This is very useful result and will help you to find roots of equations. Let's get started. Don't forget, like us and subscribe. To formulate Bezout theorem, let us assume we have a polynomial p of x, and let us divide this polynomial by this polynomial. It's also called a binomial. And if we divide this our polynomial by this binomial, we will have watch our previous tutorial on how to divide one polynomial by another polynomial. We will have x minus a times some another polynomial q of x plus a remainder. And as we already know, degree of this polynomial r of x must be less than degree of a divisor x minus a. But degree of divisor, degree of our divisor x minus a is 1. So this is 1. That's why degree of remainder r, which is less than 1, must be 0. And our remainder must have the form of some constant times x to the power 0, which is 1. Or this is just some constant r. And since, let's do it here, using this representation, call it representation 1, we have, it follows from representation 1, instead of this r, if we put the constant r, we will have p of x is equal to x minus a times q of x plus some constant r. This is a constant, some number. And that's why if we put, instead of this x, we put a, we will have p of a is equal to a minus a times q of x plus r. Because this a minus a is 0, this part will be equal to 0. And we will have that p of a is equal to r, which means that our remainder r is equal to p of a. This is the result of French mathematician Bezout. And let's formulate our theorem. Bezout, it was this result of this year's, I'm writing here, Bezout theorem. A remainder after division of polynomial p of x by binomial by binomial x minus a is equal to p of a, or the value of our polynomial at the point a, where a is a constant. Let's repeat it. Remainder after division of polynomial by a binomial is equal to this constant, which can be calculated as a value of our polynomial at a. Let's assume an example. Let's give an example. Assume we have a polynomial p of x is equal to x to the power 3 minus 3x squared plus 5x minus 1. Assume we divide our polynomial by this binomial, and we have to find a remainder. Find remainder. Easily using previous theorem by Bezout theorem, we have that remainder r is equal to our polynomial p at the point 2, and this is equal to 2 to the power 3 minus 3 times 2 squared plus 5 times 2 minus 1. If we calculate it, it will be equal to 5. So using Bezout theorem, we can easily find remainder after division of our polynomial by this binomial. Let's check it using previous technique on how to divide one polynomial, x to the power 3 minus 3x squared plus 5x minus 1. And let's divide it by a binomial x minus 2. I will do it quite quickly. If you don't understand it, watch our previous tutorial. We perform a subtraction and we have a cancellation here. It will be minus x to the power 2 plus 5x minus 1. Now here we have minus x, and if we multiply this minus x by this divisor, we will have minus x squared plus 2x. After a subtraction, we will have 3x minus 1. And here we have to write plus 3. We will have 3x minus, not minus 1, but minus 6. And after subtraction, we have cancellations here. And minus 1 minus minus 6 will be 5. So after manual calculation, we also have a remainder 5. That's why using Bezout theorem, we can easily find remainder after division of polynomial by a binomial. Once again, it's very important to understand that when we divide our polynomial by this binomial, degree of remainder must be less than degree of this divisor, x minus 2. And degree of divisor x minus 2 is equal to 1, That's why degree of a remainder must be less than 1, which is 0. It must be a constant. So this is always a constant. We found this constant. It was 5, and we checked it using simple long division, and we proved that this is really number 5. Let's continue and give a very important corollary of Bezout theorem. First of all, we have to define what is the root of our polynomial. Let's give a definition. Let's give a definition. Number A is a root of polynomial p of x, or we can equivalently say that this is a root of equation p of x is equal to 0. This is the same thing. The root of this polynomial means, by definition, this is if and only if when p of a is equal to 0. So when we insert number a in our polynomial and it will be equal to 0, then number a is a root of our polynomial, or this is the root of this equation. Graphically, this looks like this. Assume we have the chart of our polynomial. This is the graphic of our polynomial, and this intersection, assume this is the number a. Assume this is number a, and that's why here number a is root of our polynomial, because when we insert number a in our polynomial, we have 0. Very important corollary of our Bezout theorem